Okay, good morning and welcome to our EE Colloquium. I am pleased to introduce today Professor Bhaskar Rao from Electrical Engineering at UC San Diego. So let me tell you a little bit about Professor Rao before we get started with his talk. He received his bachelor's degree from IIT in 1979 and his MS and PhD in 1981 and 83 from University of Southern California. And since that time, he's been at University of California, San Diego, and he's now professor of electrical engineering. He's also a holder of the Erickson Endowed Chair in Communications at UCSD, and he's a former director of their famous wireless center, the Center for Wireless Communication, or CWC. So Professor Rao has been working in digital signal processing, in advanced communications, applications of estimation, now biomedical signal processing. He's a fellow of the IEEE for some of his work in signal processing. And he also holds a number of best paper awards, and one of them forms the basis of the talk here. So let me just mention those briefly, because it's kind of interesting. They're in three different societies. He's got the 2008 Stephen O. Rice Award from the Transactions from Communication Society from his work on MIMO communication. His 2012 Signal Processing Society Best Paper Award, Empirical Bayesian Strategy for Solving Simultaneous Sparse Approximation Problems, which is similar to this talk. And also 2013 Best Paper Award at IEEE Transactions on Vehicular Technology Conference, and that's on multicellular random beamforming and scheduling. And those are co-authored with his students and some of his colleagues and former colleagues. So with that introduction, please let me let's welcome Professor Rao for his talk today. Thank you.
Thank you, Jim. Good morning, and thank you for coming. What I want to do is today talk about some of the work we've been doing in the area of sparse signal recovery. I know that many of you may not be familiar with the topic, so the first half will be a little more introductory and motivational, so that in case you find use for it in your work. Okay? And then I will talk a little more about the Bayesian methods to the more specialists in the audience. Okay? Of course, I would like to start by thanking my students who do most of the work. Okay? So they have helped me put together this talk, as well as some of the technical elements that I will cover are part of their work. Okay? So let me start with motivation. Okay? This is really my motivation for being here, and hopefully it'll also serve some motivation for you. Okay? You know, I work in the area of signal processing, and so I'm always looking for interesting applications. And I think this area has this particular technique has many potential applications. Okay? And I would like to share some. But I think really it's the experts in the domains who can probably make more of it. This is generally a toolbox. So if you're in the signal processing area, I always say the more tools you have, the better you're equipped to actually deal with problems. So this is a new set of tools that have been developed in the last 10 years. And so it's something well worth knowing. Okay? Theoretically, any subject matures. In the last 10 years, a lot of interesting theoretical results have taken place. So you have a lot of guarantees. Okay? So if you're a theoretician, there are a lot of interesting mathematical results that provide as to when these methods will be successful and so on. So there's a lot of nice theory also. My focus will be on the Bayesian techniques. I think if you look at the books that have come out and so on, there is a certain flavor to them. They do not cover this framework, so I'm here to try and convince you to go beyond what is in the literature to maybe look at Bayesian techniques for this particular problem. Okay? So the outline. I will talk about the problem itself and then some extensions. I will not cover the extensions in detail, but the reason I cover the extensions is simply to show you what is possible, and then maybe for you to think about how you would extend these ideas, and maybe the Bayesian techniques will be an easy way for you to extend them and convince you that the Bayesian techniques are the way to go. Okay? I'll talk a little about applications so that you can see the flavor of the applications. And then the technical part will be really the Bayesian methods. Okay? So I will talk about map estimation, which maybe most of grad students who have taken a class in estimation are familiar with. Okay? And then I will talk about empirical Bayes, the technique that I think are the latest and probably the best in this class. Okay? And I will end with a summary of the results. Okay? So what is the problem? Okay? I know there are many students here who are seniors and first-year graduate students, so I think hopefully this problem is something you've seen before. Okay? This is a linear system equations, okay? And you may be wondering what else is there in linear systems equations to actually work on. Okay? And that was my reaction, by the way, when I first saw this problem 20 years ago. Okay? So when I first experienced this problem, I said, what else can you do with linear systems equations? Okay? And here I am 20 years later still talking about it. Okay? So here you have a system equation. There are n measurements. Okay? So y is your measurements. Okay? And phi is what I'll refer to as your dictionary matrix or the sensing matrix if you're in the compressed sensing area. Okay? So y and phi are known to the user. Okay? And what is of interest is x. Okay? And what is special about this system equations is you have fewer equations than unknowns. Okay? Typically, if you've taken a class, you'll probably use least squares and things of that kind where you have more equations than unknowns and you're trying to find a least squares fit. Here you have actually more unknowns than equations. Okay? But what makes this interesting is that there is some extra structural information about x that is known. Okay? And what we know is that x, most of the entries are 0. Okay? You just don't know where they are and how many often. Okay? And what you would like to solve is for this x given y. Okay? So let's try and figure out what is the difficult part of this. Okay? If I told you which entries were non-zero, then this problem is really trivial. Okay? Because you just throw away the columns that correspond to the 0 entries and solve a smaller system equation. So that's a much simpler problem to solve. Okay? But here we do not know where these non-zero entries are, and so that becomes a combinatorial search. And I will show you a little more details in a few minutes. Okay? And then V is the measurement noise, and in this talk I will assume that the noise is Gaussian, zero mean, and has independent components. But you can change the statistics. That's not very important for this talk. Okay? So what we would like to solve for, first if you think about this problem, since you have fewer equations than unknowns, there are possibly infinite number of solutions, okay? As long as the system equations are consistent. Okay? So what we're trying to figure out is how to actually search among these infinite possible solutions to one that we want. Okay? And the one that we want is the one where most of the entries are 0. Okay? So mathematically, that's quite easy to state, actually. Okay? So here's the statement of the problem. Okay? We would like to minimize the number of non-zero entries. We just simply count the number of non-zero entries. The indicator function is just simply 1 if the entry is non-zero, is 0 if the entry is 0. Okay? So we want to minimize the number of non-zero entries that satisfy this system equations. Okay? This would be the case when there is no noise, or you can think about this as high signal-to-noise ratio. Okay? By the way, feel free to ask questions. I'm happy to answer them as I go along rather than waiting to the end. Okay? If you have noise, then we'll solve the same problem, but we'll allow for a model mismatch, and that will depend on how much noise you have in the system. So we'll again like to solve for the system equations. Okay? Okay. So this is the basic prototypical problem in this context. So if you're looking in the area of sparse signal recovery or compressed sensing, this is the basic problem. Okay? Let me talk about a few extensions so that in case you have some applications where maybe this particular problem may not be quite suitable. Okay? There's one what's called block sparsity. Okay? This has applications in communication, for instance. Okay? Or in speech modeling, if you're in the speech area. Then the problem of multiple measurement vectors. This is where you have an array of sensors and you make a sequence of measurements. Okay? And then you can combine these to come up with slight variations. Okay? These are not just the only variations, but this is the ones I think that motivated what we are doing in our work. Okay? So let me spend a minute or two on this. Okay? So here's the block sparsity. Now the non-zero entries occur in blocks. Okay? So rather than single entries, they occur in blocks, and you're searching for a solution with non-zero blocks. Okay? And you could actually spend a lifetime here. Okay? There are many variations on this problem where you have equal blocks, unequal blocks, the block boundaries are known, the block boundaries are unknown. So there are many variations on this theme, but this would be an interesting variation on this problem. Okay? If you're in communications, you may want to think of this as multipath. The multipath occurs in clusters, and you're looking for these clusters of multipath. Okay? If you're in speech modeling, then we know we model speech as a excitation through a linear filter, and the excitation has a pulse form. The glottal pulse usually has a certain width, and so you will model them as blocks. Okay? By the way, my knowledge is very limited to communications and speech processing, okay? But I think these topics have much wider. So the mathematical basis, I think, has significant more potential. Okay? Here's the multiple measurement vector problem, where instead of one measurement vector, you actually have L measurements. Okay? And the way you may want to think about this is you have an array of sensors, and the number of sensors, you're making a sequence of measurements, and from this array of sensors, you're trying to make some inferencing. Okay? And phi may come from the physics of the problem, or maybe you chose it somehow. So I will talk about both these variations. Okay? The important part here is now you're not looking for non-zero entries, but you're looking for rows, non-zero rows. Okay? So you have structure across the rows, and you're trying to solve for non-zero rows. Okay? So you may wonder, when I finish this talk, I will probably not say much. I won't have time to really talk about the mathematics behind this. Okay? But you may want to reflect on how you would take what I talked about and extend. Okay? And my view is, if you use a statistical approach, modeling for structure across time will be very easy, or across these rows. Okay? All right. So let's spend a few minutes on applications, okay, so that this provides you some idea of where these may be useful, find use. Okay. This list, by the way, grows. So if you go to any conference, be it communications or signal processing, you'll see lots of papers now with a lot more applications of these tools. Okay? And this is simply because more people are aware of this particular set of tools. Okay? So I list here a number of applications, so maybe something here may catch your fancy, okay? And I will elaborate on a few. Okay? So let me start with one. I was told there were senior graduate students or senior students here, so I picked zero-pattern FFT, or the DFT example. Okay? The motivation for this is to indicate that maybe you've seen this problem but just never recognized it. Okay? And this is really a favorite pastime of mine. I go back and revisit all my old problems and ask, can I do any better with the knowledge that I have now? And it turns out every problem that I've visited, I've been able to make a difference. Okay? So I want to bring to your attention, probably if you've taken a course in signal processing, you probably took the FFT of a signal, and you probably padded zeros. Okay? And that is exactly the problem fits in this framework. Okay? So let me try and elaborate. Okay? And I picked an example from Oppenheim and Schaefer. Okay, if you open up chapter 11, a signal with two cosines, okay, omega 1 and omega 2. And you're given, in this case, I just assumed 64, just arbitrary. Okay? And you want to find omega 1 and omega 2. Okay? So maybe I will pose this question to you. How would you find omega 1 and omega 2? Anybody? Anybody taken a DSP class? Okay, let me suggest a solution here. And maybe what you do is you take the DFT and look for peaks. Okay? So you just simply take the Fourier transform, and you look at the peaks in the Fourier transform, and you hope that you will identify these frequencies. Okay? And many of you probably did this. You took a DFT of size 64 first. Okay? Were not happy. Okay? And then took a size 128. Okay? Then maybe you're not happy still. Then you took a DFT of 256. And nowadays, we have a lot more computing power, so you're free to do whatever size DFT you want to do. Okay? This exactly fits into this problem if you think about it carefully. Okay? Because you have 64 samples, and you're trying to identify 256 frequency components. Okay? You have more unknowns than the number of measurements. Okay? So what you have to ask yourself is, what did you do, or what did the DFT give you? Okay? Questions. Okay? This is really, I won't answer these questions. Okay? I just want to keep you engaged. Okay? Just to point out, there are many problems that we see, and we probably ignored the consequence. What is the result of the zero-pattern DFT? Okay? Probably many of you have been, there are a lot of explanations to this. Okay? But what I'm really interested in is in this context. Okay? When you view this problem as solving a linear system of equations, an underdetermined linear system equations, what is the solution you're getting? There are infinite solutions, and the FFT gave you one solution. Which one is it? And is that the desired one? Okay? Did you get the right one? Okay? Because as soon as you solve a 256-point DFT, you really had infinite choices, and you picked one. Okay? And the question is, which one did you pick? Okay? All right. So I will try to explain to you, maybe towards the end, try to resolve this mystery if you haven't thought about it this way. By the way, I taught DSP for 15 years before when I started doing this, I said, what is the DFT doing? Okay? And that's the first time I actually asked myself this question. So if you haven't asked this question, probably a good time to ask this question. Okay? And flexibility is good. A lot of people have complained about the FFT. Now I don't complain. Okay? I just say I didn't solve the problem correctly, and I just look for the right answer. Okay? All right, so this is the basic. So my message here really is there are many applications wherein this problem arises. Either we ignore them because we don't have the toolbox, okay, or we just simply do not see it. Okay? Here's the problem that actually got us doing this in the first place. This is the problem that my graduate student went to Los Alamos to work on, and when she came back, she had this problem for us. Okay? This is imaging of the brain. And what you have here is you make measurements on the scalp, okay, of the either electrical signal or the magnetic signal, and you're trying to model activity in the brain. Okay? So you have an array of sensors on the scalp, and you remember the real estate on your head is small, so you cannot put too many sensors. Okay? So the number of measurements is limited. Okay? So the number of measurements is simply limited by the number of sensors you can have on the scalp. Okay? But the resolution with which you want to image the brain is very high. You want a very high resolution image of the brain. Okay? So that means the number of unknowns is very large. Okay? So we are down to this underdetermined problem. We have no choice, really, by the physics. Okay? But you do have a forward model based on the physics, phi. Okay? What is known is that the activity in the brain is localized, and this is where the sparsity comes in. Okay? So we know that the activity in the brain has areas of the brain that are active, a small number, and you're trying to really solve this inverse problem. Okay? If you're in communications, then channel estimation is something you always do. Okay? And here's an example of a channel impulse response, which has a large delay spread, but mostly zero. Okay? And often in communications, you will send training signals to learn the channel. Okay? If you know that the channel is mostly zero, how would you benefit from this training? Okay? No talk in this area would be complete without compressive sampling. Okay? This is what really got this field going in the last 10 years. A lot of excitement because of this development. So I want to share with you this particular one. And the problem is as follows. You have an image B, okay, and you want to compress this image. Okay? This is the typical example that is given. There are many variations on this. Okay? So often if you are in image processing or any of these video compression, you'll do a transform. And psi is your magical transform that transforms, and the transform domain, most of the entries are 0. Okay? And that way you only transmit x. Okay? At the receiver, you construct b by psi x. Okay? So the question that was asked, if we already know x is sparse, why bother to collect b in the first place? Okay? So this is an interesting question. Okay? We already know b is sparse in some transform domain. So why did we collect b? Can we collect less information, okay, and still be able to recover b? Okay? So this is the idea. Do not collect b, but collect y. Okay? And y is a transformed version of b, a times b. Okay? And transmit y. Okay? Now, if you think about it, now what we have done is a times psi is phi. We have to solve for x. Okay? So here's the recovery problem. We'll solve for x using phi x equal to y. This is an underdetermined system equations. Okay? But we know x is mostly 0, so we can solve for this. And then we reconstruct the image by doing b times psi x. if you reflect on this, by the way, if you worked in image processing, you really realize how big an impact this has. Okay? Let's try and understand the ramifications of this. Okay? If you look at any coder, if you look at your mobile device, either speech coding, image coding, all the hard work is in encoding. Okay? The decoding is very simple. Okay? Here, the problem is reversed. Encoding is trivial. Decoding is a nightmare. Okay? This is quite desirable, particularly if you have a asymmetry in the devices that are communicating. Think about your handset communicating to your base station. The base station is very powerful. It can do a lot of computing. Okay? You want your handset to do very little, okay? Which means you want your encoding to be very simple. Okay? But let's say the base station is communicating with you. You want the base station to do all the work. Okay? So you would like this asymmetry. Okay? So this has completely changed the way you would do compression. Okay? You do not have to think about the encoding being difficult and decoding being simple. You can reverse this thing. Okay? The decoding is difficult because you have to solve this problem. Okay? Psi x equal to y. Okay? And then you construct the image by b equal to psi x. Okay? So here there are two issues. Okay? One is you're trying to solve phi x equal to y with the constraint that x has mostly zeros. Okay? And then you need to design this matrix A. You have flexibility in A, so how do you design A? Okay? So when you think in terms of compressed sensing, sometimes compressed sensing is used very loosely. Okay? When you have compressed sensing, there are two elements to the problem. One is, how do you choose A? Because that's something you have freedom over. And the other one is, how do you solve phi x equal to y? Okay? Today, I'm going to only talk about phi x equal to y, how to solve phi x equal to y. Okay? Because that could come about by nature or by design, like here. Okay? It doesn't matter where it comes from. You still would need to solve this system equations. Okay? All right. So let's talk about why this problem is difficult. Okay? It's after all a linear system equations. Why is it difficult? Okay? So it turns out if you want to find the best solution, you have to search over all possible subsets. Okay? Because you know the number of non-zero entries is small, so you need to search over all possible subsets. Okay? So let's try, so it has combinatorial complexity. Okay? So here's a simple example. I have 30 unknowns, okay? 20 measurements, 10 non-zero entries. Okay? So I need to do 30 choose 10. Okay? That's the number of combination subsets I need to search. Okay? That is actually bigger than 3 to the 10. Okay? So even a problem like this, if you had to find the optimal answer, it's just not possible. And this is really small numbers. 30 and 20 is extremely small numbers. If I now change them to 10,000, you would not be able to actually solve this problem in an optimal manner. Okay? So there are clever techniques that people have tried to do, okay, which is, one is these branch and bound techniques, where you try to search, but you try to search in some clever manner. Okay? Even then, you cannot bound the complexity. The complexity is not bounded. Okay? If you're an optimization expert, then you'd probably like to apply some optimization theory. But it turns out the indicator function is not continuous. Remember, it was on or off, and so you cannot really differentiate that function. Okay? So it's not something that you can easily optimize, and so you need more tools. Okay? So the bottom line, this is good for engineers, by the way. Okay? So you have to find low complexity methods with acceptable performance. And acceptable performance is clearly a criteria that will be domain specific. Okay? Depending on which domain you are, you have to come up with the right criteria and then ask, have I been able to solve this problem satisfactorily? Okay? It turns out in the last 10 years, under a certain set of conditions, we have guarantees that you can actually solve this problem with reasonable complexity. Okay? And that's really what has made this field even more interesting, because now we can actually have assurances that the problem can be solved. Okay? Okay. So let me just give you a glimpse of all the techniques that are there. I'm only going to talk about the Bayesian methods, so I want to just give you a sense for what else is out there. Okay? One is these greedy search techniques, where you try to search for the non-zero entries sequentially. Okay? And there's a whole class of this, and there's a whole industry. Okay? So that's certainly one approach to this problem. Okay? The other one is to try to frame an optimization problem. The original optimization problem is difficult, so you modify it to something that you can solve. Okay? So here the idea is to change the problem to something that you can solve, and then later on argue that you really solved the original problem. Okay? And the typical one here is based on what's called L1 minimization. So if you're taking a class on optimization, convex optimization, this is the kind of tools that you will bring to bear in this context. Okay? The Bayesian methods start with the statistical paradigm, okay? And that's the one I'm going to talk about today. Okay? What you make an assumption, you put a prior on the solution, because you make some assumption on the solution, and that allows you to reduce the uncertainty or minimize the search and guide the search in the right direction. Okay? So you may want to ask yourself, if you're familiar with the estimation theory, what would be a good prior to place on X so that you can actually come up with a tractable solution. Okay? And that's really the bulk of my talk, is how do you apply priors and what tools are available for solving this problem. Okay? So let's talk a little about Bayesian methods. Okay? One is the map framework, and if you've taken a class in estimation, this is probably something familiar to you. Okay? So we will apply a prior and use these map techniques to come up with a solution. Okay? The other one is a hierarchical Bayesian framework. This is less probably common, but I think this is where probably a lot of the benefits will come from. So I will try to provide you a difference between these two. What is the difference between these two? And maybe the benefits of going to a more complex framework. Okay? So my talk is organized in, I will do a two-pass approach. I'll first cover both these techniques quickly, just to give you a framework so that you have a way to contrast these two. Okay? And hopefully it'll keep you awake till the last bit when I do the hierarchical framework. Okay? So the first part is a pass just to tell you what the difference between the two is, and the second part is really the details. Okay? So here's the map framework. Okay? And this starts by looking at the posterior distribution, P of x given y, okay? And then solving for the mode of the posterior distribution. Okay? So the optimization problem simply comes up to writing the posterior distribution of x given y, and by Bayes' rule, it's a y given x, P of x. Okay? Y given x is given by the noise. So whatever assumptions you make on the noise will dictate this distribution. Okay? If you assume Gaussian, that will be a quadratic, okay, if you take the log of it. The flexibility is in P of x, okay? The prior that you place on x. Okay? So depending on what prior you place on x, you will get a different answer. Okay? And choosing the prior is really the key to finding the right answer. Okay? And if you assume a Laplacian prior, okay, you get the very common technique, which is called the L1, or the L1 technique, or the lasso. Okay? So if you're familiar with the lasso technique, in this framework, it would amount to putting a Laplacian prior. Okay? So what is the hierarchical Bayesian framework? What it does is it actually introduces one more layer of random variables, gamma 1 through gamma m, that actually control the x's. Okay? So now, instead of estimating x, you actually estimate gammas. The same map framework, but your goal now is to estimate gamma. Okay? So whatever tools we will develop for map can be applied in this context, okay, with some modification. Okay? And then you actually go after the posterior distribution, P of x given y. Okay, gamma. In some sense, this is, by the way, the standard. Most people want to get to the posterior distribution. If they can get P of x given y, then you have all you want to know about the random variable x. Okay? And then you can draw all kinds of inferences based on the posterior distribution. Okay? So in that sense, we are trying to capture the posterior distribution as a way to understand what x is. Okay? Now, why would this be any better? Okay? First, it turns out the optimization problem, the map problem, is very complex. And I will say a few words about that. Okay? So when you do this hierarchical framework, it turns out this Bayesian problem is simpler because the landscape is much more benign and the optimization problem is much better. Okay? So you get a smoothing effect. And the way to think about this is you're further away from the data, so there's a blurring. Okay? So the cost function becomes a little blurred, and you lose all the little local minima. You still preserve the global minima. Okay? So you're able to search better when you go through this hierarchical framework. Okay? This is very important. It's like, are you looking at the forest or the trees? Okay? So if you're too close, you have too much information than you need. Okay? And so by going a little further away, you see better, okay, what you want to see. The next one is really this gamma can tie several parameters. And this is, by the way, a common motivation for hierarchical Bayesian. A lot of random variables can be tied by a common parameter, so you're optimizing in a lower dimensional space. Okay? So the optimization problem is less complex. Okay? So you can actually do the same lasso problem that I talked about by using this hierarchical framework. Okay? So it turns out that a Laplacian prior can be written by what's called a Gaussian scale mixture, okay? Where your gamma, P gamma, is what you choose, and P of x given gamma is a Gaussian random variable. Okay? So you can write this hierarchical framework for the same L1 prior and repeat this exercise. Okay? This is, by the way, now one of our favorite pastimes. So when a new graduate student comes in, I say, give me a hierarchical one for a new prior. Okay? This is a good way for you to learn how to go from a type 1 or this basic map estimation to a hierarchical one. Okay? You need to come up with a representation, and then you apply. And you're surprised. The same problem, you get better results by just going to this hierarchical framework. Okay? And I'll talk a lot more about these Gaussian scale mixtures. Okay? So that's the real difference between the two. Okay? They both solve a map problem. So the map estimation is the same. So some of the tools that we'll use are the same. Okay? But they're applied at a different level. Okay? One has one additional hidden layer, whereas the other one is directly on X. Okay. Okay. So let's spend a few minutes on map estimation. Okay. So here, as I said, we will basically be looking for the mode. So we want to maximize P of x given y, and we will basically be doing this. Okay. And our flexibility is in P of x. This, by the way, is an industry in itself. Okay. Lots of papers have been written with everybody coming up with a different P of x, and then arguing why their choice is superior to the others. Okay? But the nice thing about this framework is you can learn this from the data. Okay? So if you have a application and you have lots of data, then you can actually collect data and learn P of x from the data. And once you have this prior, you can incorporate this in the actual testing phase. Okay? So there are many options. Okay? There are many options to promote sparsity. Okay? And that simply amounts to looking for P of x. Okay? And in the last 10 years, many new tools have come up for solving this optimization problem. Okay? So there is no dearth of techniques for solving this. Okay? And if you are a fan of L1, then you choose a Laplacian prior, and you still are doing L1. The reason I say that is L1 is very popular. Okay? So you will find a ton of literature on L1, okay? Which is why I talk very little about L1 here. Okay? I want you to, if you're working in this field, I want you to move beyond L1, because I think there's a lot more interesting possibilities when you go beyond L1. Okay? So here's a little more expansion. Because I need to tell you how to choose P of x. That's really what this boils down to. How would you choose P of x to get the desired solution? Okay? So we take the log. This is very typical. And then you get, I wrote a quadratic because I was assuming the noise is Gaussian. And then I assumed a prior where P of x is separable. That means all the components are independent. And that gives me G of xi. Okay? So this is the standard technique where all the x's are assumed independent. So I can write the joint density as a product of the marginals. Okay? And that's log of P of xi. Okay? So what is our problem? Our problem is, how do I choose Px or how do I choose Gx? Okay? And we want to be able to facilitate sparse solutions. We want solutions. When we solve this problem, x hat will be mostly 0 and a few non-zero entries. Okay? Once we have achieved that, then we have to argue, did we get the right answer? Okay, that's the next step. Okay? So here's the main result that tells you how to choose this prior. Okay? So what it says is your G, and you only need to focus, the G's will be symmetric. So you only focus on the positive odd-term. So for x positive. Okay? And what we're saying, it needs to be non-decreasing and a strictly concave function. Okay? So as long as G of x is a non-decreasing concave function, this optimization problem will have minima that are sparse. Okay? And the number of non-zero entries will be no more than the number of measurements you have, n. Okay. I think if you've taken a course on optimization, you're probably wondering, this doesn't look like what I learned. Okay. We have a whole course on convex optimization. I don't know if you have it here. Okay. I know Professor Fazal is here, and so probably there's a course on convex optimization. Okay. We have one at UCSD where we spend a whole quarter on convex optimization. Okay. Here it's a concave. Okay. So immediately people run away from this problem saying, you open up books, no, most books don't even have a word on how to minimize a concave function. Okay. They will always tell you how to minimize a convex function. Okay. You have to look hard, actually, to find results that tell you what happens when you try to minimize a concave function. Okay. And unfortunately, we are faced with that problem. Okay. We have to minimize a concave function. Okay. So let's look at a few special cases, things that we probably did in the past. One is, assume P of x is Gaussian, and you'll get a 2 norm. Okay. This is very common. Okay. This is probably 10 years, before 10 years, this is what everybody did. Okay. Put what's called a regularization term, which is a 2 norm, and then minimize this. Okay. And people use the argument that the solution has to have minimum energy. Okay. In fact, this is what the DFT does. Okay. So if you go back and revisit the DFT, it turns out it is actually finding a solution with the smallest 2 norm. Okay. So that's really what the DFT does when you pad zeros. So you may want to go back and see if it's possible for you to prove that. Okay. This is what the Laplacian prior does. Okay. Puts an L1 penalty. Okay. This is like the best of both worlds. Okay. This is a convex optimization problem. So if you took a class on convex optimization, saying, boy, I know how to solve this problem. Okay. It turns out the 1 norm is both convex and concave on the positive octet. Okay. So if you're talking optimization, you should say convex. If you're talking this problem, you say concave. Okay, because you can just, both are correct. Okay. So this is right at the boundary where you have the advantage of convex optimization and still be able to get sparse solutions. Okay. Which is why this is very popular. Okay. This is a very common technique used for solving this problem, because you get the benefit of optimization theory along with the results that you want, which is sparse solutions. Okay. And people have been using L1 for many, many years. Okay. Only in the last 10 years were we able to show that this L1 will actually give you the sparsest possible solution under a restricted set of conditions. Okay. But I think we can do better. That's really what I would like to say. You can do better. Okay. If you like L1, at least try the hierarchical one. L1, but in the hierarchical framework, and you will get better results. Okay? But you can do better by changing this to a slightly different concave function. Okay? So here are distributions that you want to get, okay, pictorially. What you want is a peak at 0, because you want most of the entries to be 0, and then you want heavy tails so that a few of them will be non-zero. Okay? So the green one is the Gaussian. Okay? The red one is the Laplacian, which has a bigger peak. Okay? And if you make p smaller than 1, you'll get this blue curve, which is p equal to 0.5. Okay? So you can look in the Gaussian class, if you wish, super Gaussian class, and just change p. Okay? This was a good, by the way, the last 10 years, a lot of people have tried lots of priors. Okay? So here's an example of some priors that people have done. G of x is a log of xi squared plus epsilon. This is a work by Chartrand and Yin. Okay? And the log is a natural candidate, particularly probably in optimization, people use this as a barrier function. Xi becomes 0, it's become minus infinity. So log is quite a nice function for getting sparsity. Okay? Then by Candice and Boyd and group, log of xi plus epsilon. Okay? We have looked at xi to the p for p less than 1. Okay? Once you make p less than 1, it's all concave. Okay? So you really have a challenging optimization problem. What is the difference? Different choices favor different levels of sparsity. Okay? So one will be more aggressive in promoting sparsity, while the others are a little more tepid. Okay? So the question is, which sparse prior to choose? Okay? So I will give you some pointers because I don't have time to go through the details. Okay? And I'll do this with the help of this simple one with P, where P could be 2, we know is no good. P equal to 2, by the way, is a very democratic solution, the Gaussian one. It wants everybody to participate, so you will find that nobody is 0. Okay? Everybody has a small non-zero entry. Okay? So if your goal is to get sparsity, then 2 norm is not it. Okay? You want a solution where a winner takes all, okay? Where in that case P equal to 1 is where you can start and then go P smaller and smaller. Okay? Okay? There are 2 issues you face with this discussion. One is if P is too sparse, that means if you are very aggressive, you make P very small, you have a lot of local minima. Okay? So this optimization problem becomes more difficult. And you get stuck in local minimas, and so you will never get to the true solution because you're stuck in these local minima. Okay? Which is why people like P equal to 1. Okay? They didn't have this problem. Okay? If P is not sparse enough, okay, then you may get to the global minimum, but it may not be the sparsest. Okay? So these are the 2 challenges, or the 2 points that you can think about. Okay? You know where you want to go to, which is you want to go P to 0, but you don't know how to get there. If you make P small, you will get to the bottom of the bowl, but you will get to the wrong bottom. That's not where you want to be. Okay? So there's 2 balances that you need to strike in solving this problem. Okay? So how do we solve this problem? Okay? I will give you some clues, but not the details. Okay? Because I do want to talk a little about hierarchical Bayes. I notice I only have 5 minutes. Okay? Okay? So first is there are a whole class of algorithms available. So this is what are called reweighted L2 and reweighted L1 algorithms. Okay? So this is a rich class of tools that are available to solve functions where G is concave, okay, on the positive arctant. Okay? So if you're using L1, I recommend the reweighted L1. You will be very pleasantly surprised, okay? Because it has all kinds of, the results are always better than the L1 on most numerical experiments. All these techniques are based on this majorized minimization techniques. Okay? What you do is this part is convex, so no problem. You don't have to worry. Okay? This part is concave. You don't need to worry. So what you do is you replace it by an upper bound, which is convex. Okay? And then you have a convex optimization problem. Okay? So for instance, if you replace this by a line, it will be an L1. If you replace it by a quadratic, you will get L2. That's really all there is to this approach. You upper bound by either a line or a quadratic function, and each one of those will be a reweighted L1 or a reweighted L2. Okay? And the idea is very simple, actually. Here's the function you want to minimize. Too difficult. And if this is your current solution, you upper bound by a nice smooth function, and you minimize this smooth function. Okay? And when you minimize this, you can show that you'll always do better on the original function. Okay? This is the basic theme behind majorized minimization techniques. Okay? And in this context, it's very simple because concave functions can easily be majorized by a supporting hyperplane. So you can write a simple line to do this problem, or you can do a little better by going quadratic if you want. Okay? So there's a whole slew of techniques that come up by doing this technique. Okay? I'm going to skip, my apologies here for the details, because I do want to spend a few minutes on the hierarchical one. Okay? Why should you go hierarchical? It turns out these techniques have too many local minima. Okay? So there are as many as m choose n. M is the number of unknowns, n is the number of measurements. Okay? So you have the landscape is very treacherous. Okay? So when you try to solve this optimization problem, the chances you'll get stuck in a local minima can be pretty high. Okay? Is that an issue? Clearly, theoretically, it's an issue. Practically, it may not be, okay, because you can always initialize properly. Okay? So if you're an engineer, even this should not prevent you from using them. Okay? Because in most engineering applications, we can find a way to initialize the algorithm by some other technique. We find an approximate answer, and then we use that as initialization. If we are in the basin of attraction, then we will get to the global minima. Okay? So the key really is, if you're going to employ these, is to start with a good initial condition and use some other tools to initialize. Okay? So let me try to say a few words about the hierarchical Bayesian technique. And these go under the title Sparse Bayesian learning. This was the first work was done by Tipping at Microsoft. Okay, so they were applying this for pattern recognition. Okay, and then it has now become a standard tool in signal processing for compressed sensing. Okay. So what we are here in the map, we were looking at the max, the mode. Okay, but now we will actually go after the posterior distribution. Okay. So we want to go after the posterior distribution. So we really want to know what is P of x given y, if we can, and approximate this posterior distribution. Okay? This is actually, everybody wants to do this, so it's easier said than done. Okay? So this is something that most people in Bayesian literature want to do, find the posterior distribution. Okay? So we need something tractable that can get us there. Okay? So this is what I showed you before. We're going to introduce a layer, gamma 1 through gamma m. Okay? Come up with this hierarchical representation and solve for gammas. Okay? So we'll solve the same map problem, but rather than solving for a map of x, we'll solve for a map of gamma. Okay? And once we get gamma, we'll actually try to find an approximation for the posterior distribution. That's the strategy. Okay? We will solve for the gammas. Once we found the gammas, we'll fix it and get the posterior distribution through an approximation. And this is the key. Okay? If you're in signal processing, by the way, this is one of the more newer models, I think, okay, which I think will find a lot more application in the future. For in order to do this, we need something mathematically tractable. Okay? Because we can always say what we want, but we must be able to solve the problem we want to solve. Okay? And the key lies in this Gaussian scale mixtures. Okay? The magic word is the word Gaussian. Okay? If you are in statistics and you've taken any courses, the only problems probably you can solve by hand are problems that involve Gaussian random variables. Okay? If you took a course in probability theory, probably 3-4 weeks on Gaussian random variables, because those are the most mathematically tractable. Okay? So in some sense, this is an extension, but a clever extension that still stays within the Gaussian framework. Okay? So what does that mean? So what we will do is we'll say that all these densities can be written as a Gaussian random variable, which is P of xi given gamma. Given gamma, P of x given gamma is Gaussian. This is zero mean with variance gamma I. And there's a distribution on gamma I. Let me try and elaborate, okay, before I do that. So the way to think about this is gamma I controls the variance of the Gaussian random variable. Okay? So you generate the variance as a random variable using this distribution P gamma I. Okay? Once you generate the variance, then you generate a Gaussian random variable with that particular variance. Okay? And that's given by this. Okay? So conditioned on gamma, everything is Gaussian. Okay? And that's what makes this framework work. Okay? So I want to emphasize this because this is really the key to all the mathematical beauty of structure that comes up. Once you're conditioned on gamma, everything is Gaussian, everything can be written in very nice closed form. Okay? Even though I may not have time to show you, that's really the reason why this works. Okay? And this is really what makes it even better, that all the priors that people have tried actually can have a Gaussian scale mixture form. Okay? So all the densities that people tried can be written in Gaussian scale mixture form, so immediately you can try this hierarchical framework. Okay? Here's an example. If you have a Laplacian density, which is the L1, then I already showed you this is P gamma. By the way, let me make one more observation here. Choosing Px is like choosing P gamma. So I just transferred the problem, probably punted. So choosing Px, and now I'll choose P gamma. Okay? And that will indirectly give me Px. Okay? So here's the corresponding P gamma for a Laplacian density. Lots of people have tried the student T distribution, and there's a corresponding P gamma. Okay? And if you open up the statistics literature, you will find lots of examples of Gaussian scale mixtures. Okay? 5 years ago, I didn't care about them. Okay? I would see them and I just say, who cares? Okay? Now I keep looking for examples, and almost all examples that I see are Gaussian scale mixtures. Anything away from Gaussian, you can write them probably as Gaussian scale mixtures. Okay? The generalized Gaussian, that is x to the p, also has a Gaussian scale mixture form. So there's a whole, so now if you search for Gaussian scale mixtures in Google, you will get lots of papers in the statistics literature, and they have a whole bunch of density functions that have this representation. Okay? Which means whatever I tell you can be applied. Okay? So let's go and how do we apply this? This is the problem we're trying to solve. Okay? By the way, the details are not important. So I will try to give you the high-level view so that you can fill in the details. Okay? If x was Gaussian, this problem is trivial. Okay? Because v is Gaussian, x is Gaussian, y by linear transformation is Gaussian, everything is Gaussian, you can write all kinds of distributions. Okay? So if I asked you what is p of x given y, it's easy to write. Okay? So once everything is Gaussian, it's trivial. Condition on gamma, x is Gaussian. Okay? So once I condition on gamma, this is all Gaussian, so I can write this in closed form. Okay? So the mathematics becomes very tractable. Okay? So here's the map estimate. I want to solve for gamma, which is p of gamma given y. Again, we apply Bayes' rule. P of y given gamma. This looks exactly the same before. In fact, gamma has been replaced with x. Okay? P of gamma is my choice. Okay? P of y given gamma, once you give me gamma, x is Gaussian, this is Gaussian. Okay? So I can write it in closed form, and you can write the exact version of this. Okay? As I said, the details you can work out, but the key observation is condition on gamma, everything is Gaussian, so you have a nice closed form expression. Okay? It turns out this part is convex, this part is concave, okay, in gamma. Okay? So you get sparsity again because there's a concave part and there's a convex part. Okay? And you can actually show that you will get sparsity by virtue of this optimization. Okay? Often people will say, this is how do I choose p gamma? The best way is to not do anything about it. Okay? Just simply make it non-informative so that this is dropped from the optimization itself. Okay? But you're free to choose p gamma if you have some knowledge. Okay? All right. This is what I mean by the mathematical tractability. If you give me gamma, once I solve for gamma, p of x given y, condition on gamma is Gaussian. I can write its mean and covariance. Okay? So I can give you the exact posterior distribution condition on gamma. Okay? How do we get sparsity? Because most of the gammas will be 0. This gamma is, by the way, a diagonal matrix with the gamma i's. Okay? So I will get sparsity by virtue of the gammas being 0. Okay? And there's a very nice, all the tools that I talked about can be applied, but the EM is an easy approach. So if you've learned about the EM algorithm, this is one of the nice examples where you can apply and write the EM steps in very close form. So let me end with some properties. Okay? First, we can show that the local minima are indeed sparse. That means we are indeed getting a sparse solution when we solve this problem. Okay? The important one is, compared to the map estimation, this has fewer local minima. Okay? So even if you start with the same p of x and you solve it in the hierarchical framework, you can actually show it has fewer local minima. So that means the landscape that which you're operating in is more benign. Okay? In high signal-to-noise ratios, you can actually show that the global minimum is indeed the sparsest. Okay? So that means you're solving the right problem. Okay? You just have to figure out how to get to the global minimum. Okay? And lastly, we can actually show that this is actually trying to approximate the posterior distribution of p of x given y. Unlike the map which goes to the mode, this is actually going after approximating the posterior distribution p of x given y. Okay? So let me give you a toy example just to, because these problems are hard to, when you apply to a real application, you have to know a lot about the application. Okay? So it's not very easy to convince you it works, but toy problems are easy. So here's what we do. Okay? We generate a random phi matrix, which has 50 rows and 250 columns, which means 50 measurements, 250 unknowns. Okay? Then we generate a solution x0, a known solution randomly, which is sparse. Okay? So we generate one, and then we generate, and usually the non-zero components are chosen to be Gaussian in this experiment. But you can change the distribution of the non-zero entries. Okay? That means we're generating the actual x. We know what actual x is. Then we generate the data by doing y equal to phi x0. So in this problem, we know y, phi, and x, except we present y and phi to the algorithms and ask what is x. Okay? Then we have a way to compare whether we got the right answer or not. Okay? And then, of course, I'm going to compare the Bayesian learning with the previous techniques. Okay? And we do this over 1,000 trials. Okay? And what we ask is, what percentage of the time were we successful? Okay? So what fraction of these 1,000 trials did we get the true solution, and when did we fail? Okay? So here we know the ground truth, so it's possible to actually compare. Okay? So here are the results. Okay? This is the L1. Okay? This says the x-axis is the number of non-zero entries. Okay? So this means 2 non-zero entries, 4 non-zero entries, and so on. Okay? And this is the probability of success. Okay? So you want to be up there. Okay? So what it says is if you have only 4 non-zero entries out of the 50, then you can find them with 100% success. Okay? So small number of entries is easy to find. Okay? As you increase the number of non-zero entries, the L1 fails. Okay? The red curve is a reweighted L1. Okay? And by the way, we are not the first ones to show this. This is the reweighted L1 is well known, so it clearly has superior performance. And this is the reweighted L2. Okay? And the green curve is the hierarchical Bayesian. Okay? So by going to this hierarchical framework, okay, you automatically get consistent improvement over the standard techniques. Okay? I want to leave with another example, though I haven't talked of depth, to show you the power of the Bayesian, because I think we haven't quite exploited all of it. Okay? Here, we actually generate now 5 measurements. This is the multiple measurement case, so we have 5 measurements. Okay? That means your x is now 100 by 5 in this case. So you have many more unknowns that you're trying to solve. Okay? If you go to the hierarchical framework, the gamma still is only 100. Okay? So it turns out when you tie the parameters together, you don't change the complexity. Okay? So here are the results. Okay? This is the L1. Reweighted L1, reweighted L2, and there is your Bayesian techniques. Okay? The higher is the better. Okay? That means this is the probability of success. And so by going to problems with more structure and more complex, the Bayesian techniques tend to do much better. Okay? All right. So let me end with a summary. Okay? First, I think this area has a lot of potential applications. Okay? So the applications just continue to grow. And hopefully you will find some application of these techniques. Okay? The methods are fundamental. Okay? So the whole idea of how to enforce sparsity, how to solve systems that when these problems have structure, how do you impose the structure, is something that I think most people in signal processing would benefit from. Okay? My own opinion, the Bayesian techniques are quite interesting. Okay? They offer quite a rich class of algorithms for you to pursue. Okay? You can stick to the map and go down the reweighted L2, L1, or you can go to the hierarchical Bayes and try the sparse Bayesian techniques. Okay? There's a lot of theory still to be done here, okay? Because these are just beginning, and I think if you're looking for a topic in this area, this is a great area to try and make a dent. Okay? I think these Bayesian techniques are very versatile. And can be employed in problems with structure. When there's additional structural information available, it's natural. There are natural ways in which you can impose this structure. Okay? I think I'll end here and take some questions.
Let's thank the speaker. So we have time for a couple questions, if there are any.
How would you formulate block sparsity in your Bayesian framework?
Okay. The question is, how do you formulate block sparsity in the Bayesian framework? Okay. So let me go back all the way. Sorry, I have to go back right to the front, right? So maybe it's easier done on my. So the question while I'm trying to get to the slide is to ask yourself how you do it in an optimization framework. Okay. Then the Bayesian one will be more appealing to you. Okay. So. By the way, it turns out I do this always with my students because I'm biased. Okay? But I always, when a new student comes in, I give them a problem and say, here are the 2 frameworks, which one would you apply? It turns out most people can tell me the answer on the Bayesian without leaving the room. And the other way, they have to come back. Okay? So So let's look at the Bayesian question. There, okay? So what we would do is we would model this, each block, okay? There would be a single gamma that ties the block. Okay? That way the number of parameters is small. Okay? So this is really why the example I showed you, the MMV, works better. And then within the block, you can impose structure. You can put a correlation matrix if you wish, or you can make them IID. It doesn't matter. So the whole block is now related by one parameter, whereas if you try to solve x, you're treating the whole vector by itself as an unknown. So the size of the problem is much higher. Okay? It's even more dramatic when you go to this problem, because you see the size of x grows with L, okay? Whereas a single gamma controls the whole block. Okay? So when you're solving it in the hierarchical framework, you're solving for a much lower dimensional problem. Okay? So the landscape is much cleaner, and you get better results. Okay? Yeah.
Any other questions? I have one about the choice of the prior, about sensitivity to the choice of the prior.
Right.
Do you see any of that?
The answer is, in the map framework, the answer is yes. Okay? But when you go to the hierarchical framework, we almost make p gamma non-informative, and that almost says any of those priors would be fine when you make the p gamma non-informative.
So that's usually how you start out. Then.
Yeah, that's how we start.
And then that's good enough.
At least for this problem.
Right.
But I do think in applications, that may not be the right thing to do. If you have priors are a good way to guide your solution. So if you have knowledge and you believe in the knowledge,
right.
then it makes sense to put it in. Okay?
Right.
So in that sense, I feel that if you can learn p gamma from data, then you should learn it and include it in the optimization.
Okay. Yeah. Any other questions? Okay. Oh, wait, we have one more.
Okay, so you're talking about hierarchical networks, and you went only like 2 depths.
Yes.
Do you think there's any benefit of going higher?
I think no. I think if you go further away, the blurring is then the landscape becomes too flat. So you may actually not be able to do the optimization properly. Okay? So people have tried this, even in the machine learning literature, when you go and look at them. As you go further away from the data, the information from the data and the variables is too small. Okay? So it's very hard to actually extract information as you go further away. Okay? One more layer may be okay if you can tie too many parameters. If there is, see, as you go further away, you want to reduce the dimension of the parameter space. Okay? If you're able to do that effectively, maybe, okay, one more. Okay? I am skeptical that you can go further and get better results. Okay,
Okay. Thank you very much, Bhaskar.